So, more precisely, BFS is a way to find all vertices reachable from a single vertex S. So, it has a source. And how does the algorithm work? So, for V in V minus S, we are going to color it white. And we are going to have color of S is gray. And there is a Q which is empty. So so this is the proper operation on the Q, add Q to S. So S is added to Q. So, I mean, this way of calling shields you from how really Q is implemented. Okay, so Q could be implemented as a linked list, an array, or something like that, and you are, as a user, you just say, okay, add it to Q and take it away from Q, and because it's a Q, you always take it from the front and add it to the end and take it to the front. But the way you call it, it's independent of how it's implemented. But we know that a Q can be implemented by an array or a list and support these operations in constant time. Okay. So I'm adding S, and then I say while Q is non-empty or not equal to empty, let's take, this is another operation to the Q, take the head of Q, and for V in the adjacency list of U, NQ V or to Q. So if color of V is white, then we add it to the Q, and after you are done with all the neighbors of U, I'm going to color U black. Okay, so that's all the entire algorithm is. It starts with, okay, let's see how, I want to see it done in. So this is S, 1, 2, 3, 4, 5. Then my Q will have S. So the invariant is that anything on the Q, add it and color of V is gray, right? So there are three types of vertices. White is unvisited, V is visited, but their neighbors may or may not have been explored, and black means that their neighbors have been explored. So the invariant is that anything in the Q has the color gray. Right? Started off with S being in gray, and whenever you add something to the Q, we will make it gray. So the Q in this example will start with S, then, okay, so let's look at the colors of S, 1, 2, 3, 4, 5. Everybody would be white. To start with, S would be gray, and then we take out from, well, Q is non-empty, I take the head, which is S, look at all its neighbors. If they are all white, add it to the Q and make them gray. So S's neighbors here are 1 and 2. So 1 and 2 will become gray, get added to the Q, and S becomes black because after you're done. Right? So now go back, So this is, pick the head of the Q, which is 1 here. So we look at, yep. So we look at 1's neighbors. So you have an adjacency list is where you have represented this. 1's neighbors are S alone, and since S is black, I don't add it, so there's nothing happens and 1 is out, and 1 becomes black. Okay, because 1's neighbors are all explode. Go to the head of the queue again 2, so we will remove it, make all its neighbors, in this case S and 3 or S3 and 5 are the neighbors. S is gray or black, so we won't add it. 3 and 5 will be added, so my Q will have 2 is removed, so Q will have 3 and 5 which are made gray. Okay, and then after you are done with that, 2 will become black. Then we pick the head, which is 3. We add all its neighbors, 4 and 2, but only 4 gets added, and so 4 becomes gray and 3 becomes black because we're done. Then I go to the head, in this case is 5, so 5 becomes, there's no neighbor to add, and so on and so forth. So that's, Q becomes empty and you stop. Okay. And we saw that if the graph is not connected, if you have other components, you can do the same thing. So look at a white vertex. So for, I can just write the following, right? For V in V, if color of V is white, then just do BFS of V, right? So I start with, I take the first vertex, do an exploration, and if I've finished with, if I've reached all the vertices, then everything will have become black. So then it will just run through a sort of the remaining vertices, just check them all, they are all black. Otherwise, it passes through this loop, finds the next white vertex, explores it, and then it continues, right? So it's, so we saw that overall it's order m plus n, and things we can check if G is connected, partition V into connected components, and there are more things you can do with BFS. So you can get a tree if it's a connected graph, otherwise you get a forest, what is called a BFS tree or a BFS forest. So how do I get this tree? Every time when I add somebody to the queue, I'll see who made me add that vertex into the queue, made you add that vertex into the queue, and make that vertex the parent of this. Okay. So, for example, I can say for S, it's nil, there is, S doesn't have a parent, but here, if I take U, I look at its adjacent neighbors, and if its color is white, I'm going to make it gray, and who made me gray? The vertex U made me gray, so I'm going to make the parent of V to be U. Okay. So I'm just defining for every vertex reachable from S a vertex called parent. For S it's empty. For every other vertex, how did, V became gray and got added to the queue, that means V is reachable from S. Who made me add to the queue? U made me add to the queue because I am V is adjacent to U, so I will make the parent of V U. Okay, so every node will have a unique parent, right? Many guys may have the same parent, right? All the neighbors which got added will get the same parent. So what I get in this case, so who will be the parents here? So P of S will be nil. For one got into the queue because of S, so S would be its parent. 2 got into the queue because of S. 3 got into the queue because of 2. And then 5 got into the queue because of 2 again. And then 4 got into the queue because of 3. Okay. Now you can, so what is this? This is so S has 1 and 2 as its children. So 1 has parent S, 2 has parent S, 3 has parent 2, 4 has parent, did I get this right? Yes. Okay. And 5 has parent 2. Yeah. So what I get is a tree. It's a tree because every node has a unique parent. Okay. So it's, you can, the whole tree is represented by these parent pointers for every node, because every node which is gray, which has become black, they have a pointer except S, which is the root. So if the graph is not connected, you can do it on every component, and what you get is a forest. So this is called a BFS tree, right? BFS tree. Okay. And what more, BFS actually computes the shortest distance from S to every vertex you can reach. And you can also compute the number, the shortest distance. How do I compute it? Well, I mean, why does it compute the shortest path? We will actually formally prove it because it requires a careful argument why you get the shortest path. You can see in this example that when I start from S, the shortest paths are 1 and 2, and for 3, shortest path is, 5 and get, and 4 is shortest path length is 1, 2, 3 edges. Okay. Yeah, so 4 could also have become a child of 5, but yeah, so this works fine. So it computes shortest paths, we will prove it formally, but let's see in the same code, what do I have to do to actually compute the distance as well? Shortest distance from S to every other vertex. So what do I have to do?
Usually call parent on each word. I mean, we recursively call it until we get S, and we count the number of times.
Oh, you want to what? Sorry.
So.
Oh, I see. You're saying for every vertex, follow through the parent pointer and go all the way to S, and you get whatever the number is the distance. Okay. That's a separate code. I'm just trying to say, can I do it here itself and compute it? Okay, that's definitely a way to do it because but then you need to do it for every vertex separately. But I want to see if I can do it here. Yeah. Okay. So I'm going to use another. This is the distance from S to that vertex. So for S it's 0. And then again, it's exactly like, P of V is U. So V got added to the Q, its parent is U. At that point, I can write down the distance, right? Distance of V equal to whatever the distance of U plus 1. Because if it so happens that this is the shortest path, we need to prove this, I get this thing also. Okay. So no extra effort really, the whole thing is order m plus n. We saw why order m plus n, simply because this is the crucial work here. It's the degree of U, amount of effort you are trying to do, and no vertex gets into the queue more than once because it would have become black and I won't add it. So every vertex, its degree is the total time you're going to spend. Summation degree, that's order m, and there is order n everywhere, right? We are setting the colors and there is something here. Yeah. Okay, so I'm going to say shortest paths from S to every vertex. Every vertex is reachable from S, right? So this needs a proof. I'm going to do it now. In particular, what I want to claim is the D value stored at the end is actually the shortest distance from S to that vertex. Okay, so before I do that, let's also quickly check that the whole thing works for directed graphs as well. I have been saying undirected graph, but if I say directed graph, then what is this? This notion of, adjacent vertices means that out neighbors of you, right? For directed graphs, it will be out neighbors. And that's all I have to do. There's nothing else. So I just start from our S and go to all the out neighbors, and for each one, if it's white, add it, and make it gray, add it to the Q, make its parent that U, and add the distance. So everything remains the same. And so whether the graph is directed or undirected, I want to claim that this D value stored at the end is actually the shortest distance from S to that vertex. Okay. I mean, you might want to initialize all the D values to infinity or something, right? Yeah, so this is the for loop. This is outside the for loop. So here I might just do dv is infinity, so that if a vertex is not reachable from S, its D value won't get changed and it remains as infinity. Okay, so when I say shortest distance, if there is no path from S to that vertex, the shortest distance is infinity. Okay, so consistent with that, I show that. Okay, so how will you show this? Okay, so the claim dv is the shortest distance. So clearly for distance, I mean the number of edges, because I have assumed, it's a convention, because for S I assumed it's 0. We're not counting the number of vertices. Take the shortest path and I am counting the number of edges in the path, and that's my distance. Because by convention for S I have said it's 0. Okay, so we will prove. Okay, so let's use some notation for length of the shortest path. Okay, let delta SV be the length of the shortest path from S to E. Not the, but could be because there may be many shortest paths, but the lengths are all the same. So the claim is that delta SV is actually dV, right? I'm going to argue that it's greater than or equal to dV and it's less than or equal to dV. Two different claims. Okay. So claim 1. So dV is greater than or equal to delta SV. So whatever the algorithm has after completion has stored V, I want to claim that it's at least shortest path, and then in claim 2 we will show it's exactly equal to. It cannot be strictly more. Okay. So this we will show by induction on. I mean, you need to prove this first of all. I hope that you understand that I need to prove it, because something like DFS we will see, and the whole thing is not correct. It is not true for DFS, and so it's intuitively that I'm actually growing in a breadth-wise fashion. I'm visiting all the neighbors of V first, and then the neighbors of V first, and so on. So you expect that we will get the shortest path, and we will actually prove. Formalize the intuition basically by induction on number of Q operations, whatever. Yeah, if you show that, that's good enough, right? Why is that true? Yeah. So okay, right. So what?
Can you repeat the?
Yeah, that's all I'm going to say, right? Yeah.
So what did she say?
See, what she said is, how do I prove this? If I tell you that you need to show that there is a path of this length. So that is what I'm going to show, right? There is a path of a length at least this. Okay, we will show, and that we will show by induction. We will show that there exists a path of length at least dv for each v in V. Okay, so the shortest path length must be at most whatever this length, and this we will show by induction on the number of Q operations, right? When you have not done it, so it is true for S because there is a path of length 0 from S to S, so that's a base case. Assume so when you say induction, you have to be very clear, induction on, because there are many parameters here, right? So more specifically, I'm saying I'm counting this NQ operation, which is adding to the Q, and I want to count induction on that number of these operations. When it's 0 or when it's 1, you're just adding S for which it's true. Now suppose it is true for my until the point I'm going to add this vertex, right? Assume true because dv value, okay, so first of all, if there is no path from S to V, then you won't even dv will not change at all because there is no path, and we've already argued that it is only doing the reaching thing. So dv will remain infinity, and so the claim will be true because length of the shortest path is anyway infinity. So there is, so we assume there is a path to V, so this step will be executed, and so we will get some value, some finite value, right? So assume, because V will be reachable from S, and eventually it will become gray and black and so on. So assume it is true before V is added to Q. And suppose P of V is U, right? V has been made to add to the cube because of a vertex U. So since at that time U was in the Q, by induction hypothesis, we know that there exists a path of length at least du from S to U. right? So now take that path and extend it to V, because V is a neighbor of U. And so there is a path of length at least du plus 1, right? Because U has been white. So extending that because what is dV with respect to du? Exactly plus 1, because its parent is U. And so so that means U made V to be added to the Q. So d of V is exactly equal to du plus 1. Since there is a path of length at least du, by extend that to V, there is a path of length du plus 1, which is equal to dV, right? So that means the shortest path length is at most this. Okay. So now to prove the other thing, let's write down more properties of BFS. So I want to show that it cannot be strictly more than, so it will be a shortest path, right? The dV will be the length of the shortest path. Okay, so let V1, V2, VL be vertices in the Q at some point. Okay, and all these vertices have a d value, a finite d value, right? Because once I get into the Q, you will get a finite d value, because they are all reachable from S. And in the code, if you look at the code, the moment I add somebody to the Q, I am going to make dV to be the earlier du plus 1. So everybody has a d value. The claim is this: dV1 is less than or equal to dV2. So the distances, first of all, I want to say that they are in non-decreasing order, and d of VL is less than or equal to d of V1 plus 1. Okay. So if you think of BFS is, you can think of this distance as also like levels, right? Everybody at distance 1 or in level 1, everybody at distance 2 or in level 2, and so on and so forth. Then what is this claim saying? The first claim says that the distances are in non-decreasing order. The second claim says that that's it. There are only two distances, right? The last distance is either equal to the same as this distance or just one more. That means at any point of time in your Q, there are only vertices at two levels sitting there. Okay, in the Q. Again, it's intuitive, because you finish one level and then you get to the next level, and so you will be going to the third level. I mean, you will not. We'll again formally prove this. Okay, so I want to claim that this is going to be very useful to show the reverse inequality to show that it's the shortest distance. Okay, question. So first of all, I'm just saying the distances are in non-decreasing order, and there are only two distances basically. At most two. In fact, they could all be same distance, or there may be one more. That's it. So again we will prove this by induction on the number of Q operations. Okay, when S was there, that was the only vertex, so now there is nothing to prove there. So assume it is true that I have a Q and where I had this thing satisfied. Let's see. Okay, so I had V1, V2 up to VL. I've added all the neighbors and put them in, and the property is true. Now what am I going to take? I'm going to take this V1 and add its neighbors, right? White neighbors of V1. Okay, with the +1 distance, whatever this distance is. So let's verify that these two properties will be still satisfied when I add these guys, right? So will this be satisfied? Because all these are in non-decreasing order, but this guy is at most d of v1 plus 1. Hence, when I add new vertices, I am going to increase that distance to this plus 1 anyway. So all of these neighbors will have d of v1 plus 1. So, and this is at most d of v1 plus 1 because of this claim. So this first inequality will be true, right? And I have to show that the last guy is at most first plus 1. But the first guy has changed now. Okay? But again, it should be obvious, right? Because this, so why is this? I want to show that whatever I add, let's say V new, its distance is at most V2 plus 1. I need to show that, okay? But I know what is this? This is exactly equal to dV1 plus 1, right? Because when I add them, their distance is exactly this plus 1. And we know that dV1 is less than or equal to dV2. So this follows, right?
Oh, I don't understand this second clue properly. The last vertex is
Whose distance
yeah.
is not too far apart. They are all in increasing order, but not, this is 5, that cannot be 7 or 8, at most 6 or 5. It could be that all the distances are the same. So the way you should think about it is that in your queue, the distances will be like this 4, 4, 4, 4, and then it becomes 5, 5, 5, 5. There are only two distances because the last guy is at most this plus 1. Or it could be all 4, 4, 4, 4, 4. You cannot have another distance 6 here because that would violate the property that this is at most this plus 1. So there are only two distances, two levels in the queue. Okay, so I argued it, you can by induction on them. So
Doesn't it require proof to even
I'm giving you a proof. I need to prove this, right? But what is distance of V new? Exactly df v1 plus 1. But I know that df v1 is less than or equal to df v2. So df v1 plus 1 is less than or equal to df v2 plus 1. So, so the last guy whose distance is this plus 1 is less than or equal to this distance. So in fact, you need both these to prove that these two properties are satisfied. Okay, so now what is this saying?
so in a way, for those two claims, we use second claim to
Exactly. You need both. Yeah. So I'm strengthening my induction if you like. Base case is true anyway. Both are true in the base case because it's just S.
But we can't use, like, we have to prove two things and we are using first.
I'm using only the base case. The induction hypothesis I am using. So I am adding a new vertex and I am assuming both these are true up to this point. What are these? Both these, they are in increasing order and VL is at most V1 plus 1 distance. I'm assuming that. Now when I add, I need to prove both these things. So the way I prove it is that, since VL is at most V1 plus 1 and these guys have just become V1 plus 1, the increasing order is satisfied. That's the first claim. Then I need to prove this last one and that's what I went through. Right? I need both to prove both. Okay, so I'm not assuming one and proving the other at the induction step. I'm assuming both of this up to the induction step and then I'm proving it at the induction step. Okay, so now what is this saying? That the D values are sort of monotonically increasing as they become black, right? Monotonically increasing, yes. Okay, so so some vertex is black, let's say, and somebody is gray. That means the D value of that is less than or equal to D value of this. That also follows, right? Because before it became black, it was sitting at the head, and then these guys are gray, so this is less than or equal to. So that's important. So now I want to prove claim 2, which is that it's less than or equal to. So this is also going to be sort of okay. So right, what I mean. So earlier we said if you give me the D number, I will provide you a path of that length. Now I'm saying take the shortest path and I'm going to say that that length is what you will have at D. Okay. So proof again, it's true for S. Okay. Because D value is 0. So, suppose assume some U. Okay. Assume V is a vertex for which some vertex for which this is not true. What does that mean? That D value is actually strictly greater than delta SV. Right? Because we know it's greater than or equal to, we have proved that. So suppose, and let V be such a vertex with the shortest distance from S. Right? So algorithm has stopped and it provided me D values, and I want to say that every D value must actually be equal to the length of the shortest path. Suppose there is some vertex for which it's not true. There may be a lot of vertices for which it's not true. Okay. So I pick the vertex which is closest from S. V is such a vertex. And let V U V be the shortest path. I mean, I'm looking at the predecessor of V. No, S. I'm looking at the predecessor of V in the shortest path. U could be S. Because I know for S is not such a vertex, there must be some other vertex, and I look at so U is the predecessor. Now
Since V is such a shortest vertex, the initial condition should be true for U. So du is less than or equal to delta.
du is actually equal to, yes. du is equal to, not necessarily, yeah, not less than or equal, because we know that it's greater than or equal to, du is delta SU.
Why are we insisting on equal to? We can say that it is less than or equal to.
We have already proved it's greater than or equal to for every vertex. So it's actually equal to, right? So now look at when u was being explored here, right? U would have come to the head of the Q at some point because U is in the reachable from S. Now, what was V doing at that time? And then we will argue and get some contradiction. Okay. So, and this lemma is also going to be useful. So the proof. Consider color of V when U was at the head. See, every vertex reachable from S will eventually get into the Q and become and get out of the Q. So U, when U was being explored, let's see what was V's color. Okay. Can V be white? Okay, so this is equal to and so delta SV is du plus 1, right? Because this is the shortest path. So at the time when you are trying to explore U, I want to see what is color of V. Can color of V be white at that time? Suppose it is, what would you have done? We would have added to the Q and made d of V to be equal to d of U plus 1. But you know that, we know that this is our assumption, right? Delta S of V is less than d of V is our assumption, and so V cannot be white. If V had been white, I would have added to the Q and made d of V equal to du plus 1. And remember, once, d value never changes. Once you get into the Q, and d value never changes. So d value wouldn't have changed, but so d value would have been equal to du plus 1, not really greater than if V had been white. Okay, so V could not have been white when you tried U. Could have been gray. What does gray mean? It is sitting in the Q, right? So U is at the head, V is here. Then by this property, d of U is less than or equal to d of V. You have a problem there, because we are saying even d of U plus 1 is strictly less than d of V. Right? If V had been gray, it will be like this. So yeah, so d of U plus 1 could not have been strictly less than d of V. Could it have been black? No, because again, if V had been black, its distance dV would have been less than or equal to du. Okay, which would be a contradiction here. So if V is white, d of V would have been equal to du plus 1. If it's gray, d of U would have been less than or equal to d of V, and if it's black, d of V would have been less than or equal to d of U, and all of these are contradiction to this assumption. Okay, fine. So this is, I mean, the way it's growing, the level. So this is important, that there are only two levels sitting here, and the way, this is intuitive, but this is just a formal proof to show that actually the d values it gets are shortest path. Okay.
Does this claim includes all kind of graphs? Because there may be a graph in which the first vertex would have the last vertex may not be at most, distance may not.
No, this is at any point in the queue. It's not talking about all vertices. You go to your queue and see how it is. In the queue, there are only two distances, at most two distances. Of course, vertices are coming in and going out, and the distances are increasing and so on. So it is just at any point you take a snapshot of the queue. This is the situation. Okay, so the whole thing works for undirected graph or directed graph. We do a BFS, you get the shortest paths. Now, in some cases, you may have weights on the edges. Okay, so this is an unweighted graph. A more natural modeling where you really need shortest paths are the edges have some distances. But so can you do something to use this and get shortest paths even in the case, let's even say they are positive distances. So each edge has some number, right? So your graph so this may be of distance 4, this may be of distance 2, this may be of distance 1, and this may be of distance 6. So for example, to get to u to v, in the unweighted graph, the distance would be 1, but the weighted graph, this may not be the shortest path. You are better off taking this path because it's 2 plus 1 plus 1. Okay, so can you think of a very simple fix? No, nothing clever. I mean, in fact, we will see a clever algorithm due to Dijkstra, which is a very famous algorithm, to find the shortest paths when you have distances. But is there some high level fix you can think of it and then use it as a black box to find the shortest path from edge to every vertex when your edges have distances?
So you always never take the edge which is having the shortest.
No, I'm just saying,
Every time
can you think of a way in which I can use this as a subroutine? I'm going to use this BFS as a subroutine. Take my graph, do some modification, and then call this algorithm. No, I don't even want to go and look into this. I want to use this as a subroutine. I want to compute shortest paths here from S to every vertex where the lengths are now the weighted path length. Take the graph, can you modify the graph somehow so that you can use this as a subroutine?
this graph, if they were like, the weight is 2, then you subdivide the edge. If the weight is 6, you like 5 times subdivide it.
Exactly, right? So the weight is 6, I add some 6 vertices here and then back to unweighted. So you have to, this is 1, 1, 1, 1, 1, and then I just call this algorithm. Okay. Now, so what changes? What happens? Do you get an m plus n algorithm again? Or? What is n? Or what is n now? Right? N changes because n depends on the weights. Okay, and n could be really bad. Maybe you have 10 vertices, but the weights are all 200, 700, 8,000. Then you're creating all these vertices. Summation of the weights, which is mess. But at least there is one way to do it. It's expensive, but if the weights are small, you may want to do it. But we will get to Dijkstra's algorithm, which is more clever, where basically when you add vertices, you are a little more careful about it. Okay, not just every adjacent. You look at the shortest, and we'll do something. So we'll get to that later. So before I move on to another depth first search. Yeah? Is there a question?
It is muted, the microphone.
Can you hear me?
Can you hear us, please?
No, very mild.
Can you hear us?
Yes, now we can hear you.
Yes. So I want to ask, why can't it be gray?
Why can't what be gray?
B.
Oh, we can be gray. And I'm saying in all the three cases, we arrive at a contradiction to this thing.
Yes. So how is B being gray contradicting?
Okay, so if V is gray, I claim that du will be less than or equal to d of V.
Because U was in.
Yeah, because U is in the head, V is here, and because of this claim we have proved, du will be less than or equal to d of V. And why is that a contradiction? Is that the question? But what do we know? What is our assumption? Du plus 1 is strictly less than d of V, because this means, oh, sorry, yeah, okay, good point. Not just that, there's more. We know that dV is less than or equal to du plus 1 because of this claim. That's a good point. Because of the second claim, there are only two distances, so dV is not too far, right? dV is sandwiched between du and du plus 1. So, if I look at du plus 1 is greater than or equal to dV, cannot be strictly less than dV. That's a contradiction. You need that claim as well. Okay, thank you. Because of this claim, we know that dVL is less than or equal to du. Even the last guy is, so this guy will also be less than or equal to du plus 1, and whereas this is saying dV is strictly greater than du plus 1. Okay, so before I move on to BFS, I want to capture more things about this. So I've erased my example and tree, but that's okay, I think. Let's classify the edges of BFS. So, okay, so what does that mean? What do I mean by this? So, in B, let's first look at undirected graph. You construct this BFS tree, right? Maybe something like this. This is a BFS tree. So every tree edge is an edge in the graph, obviously, right? But the graph also has more edges. Let's understand how will those edges be. Okay, so how will those edges be? Again, it's undirected. So what can you?
On the same level or consecutive levels.
Same level or consecutive level. So how are the remaining edges of graph? It could be like this. Okay, so why was it not added? So basically, what does this mean? This means that when I was exploring this vertex, I did not add. V was what? What was V's color? Gray. V was already in the queue. or it could have also been black for all you know, right? It could be like this, maybe this guy was done. So V was gray or black, and that's why I didn't, because white means I would have added, it would have become a tree edge. So V was gray or black, right? So so how are these? It's the edges can be like this. Can you have an edge like this in the graph? Yes, because you know, or rather, you know, if I have to think in terms of order, look at this. So this was in the queue, and then this guy was explored, this got into the queue. So now this was the head, and I'm looking at its neighbor. So this neighbor was already in the queue. So this is possible. But more importantly, can you have an edge like this? Can you have an edge between levels, two levels apart? An edge in the graph. Why not? Because
the lowest vertex would be in the same.
yeah, then why did I not add it here in the queue, right? Why did it wait that long? So edges are endpoints are in the same level or in consecutive levels. In particular, you cannot have edges like this. But what about in directed graph? Same again, in the directed graph, you cannot have an edge from here to here, but you could have an edge from here to here, right? Because when I was trying to explore this was a neighbor, but that was already black. So it's important be clear about how the non-tree edges in an undirected graph and directed graphs. So directed graph again in the same level, consecutive level. You could also have an edge from a descendant to an ancestor. And if the graph is not connected, and if I grow a BFS starting from here, you could also have an edge like this. From here to here, but not from here to here, because that edge I would have brought it into this component. But you could have an edge from here to here, because this was explored first, and at that time I would not have been able to explore because the edge is in the wrong direction. Okay.
When you found two disconnected components, you BFS on one level, so it will give you one connected component.
Well, in the directed graph, what do you mean by connected component? I need to strengthen it. We'll get to that later. Undirected graph. Okay.
How will we reach to the BFS tree of the second component? We'll have to give the root for the second component.
Pick. I mean, we had written a code. Pick any white vertex and explore. Right. So pick any white vertex and you will explore and you will get another component. In fact, I wrote this thing, right, for, remember, for V in V, if it is white, do BFS. So at that point, a lot of vertices might have become black, and then I go to the next white vertex and explore. Okay, here is a cool application of BFS. In fact, maybe you can even work with DFS. Suppose I want to find whether a graph is bipartite. Do you remember what you mean by a graph is bipartite? if the following happens, there exists a partition AB of V such that the graph induced on A and the graph induced on B are independent. Right, so the edges are only like this. Okay. So if I have given a graph and I want to check whether it is bipartite, this definition gives you some algorithm, right? Brute force algorithm, try all partition and check, right? Yeah, so there is an equivalent characterization. G is bipartite if and only if G has no odd cycles. Okay. Clearly, if you have an odd cycle, you cannot partition it in two because you give color 1 and put this in 2, this put 2 and this is stuck. Right? But the beauty of this characterization is the converse is also true, that if your graph has no odd cycles, then you can find two sets of vertices to partition your vertex set such that they are individually independent set. Okay. So how do you prove the converse? Okay, I mean, hopefully you have seen the proof. I'll leave it to you, but proof is somewhat involved, but we will give a proof algorithmically. Okay, so let's think of what would be an algorithm to check whether a graph is bipartite. Okay, let's say it's connected, because if it's not connected, work on every connected component and check. Okay, so let's say it's a connected graph. How do you check a graph is bipartite? So, I mean, since we have seen only BFS, do a BFS, okay? Yep.
And check that there should not be any edge, non-tree edge in the same level.
Exactly. So the algorithm is, well, I mean, we need a proof. Do BFS, and then for every edge, UV, verify that du is not equal to dv. Okay, but d is the level, right? So let's see why the algorithm is correct, meaning if this is true for every edge, you are claiming that it is bipartite, so give me the two sets of vertices which are mutually independent. Right? So take the vertices at odd level as one part, vertices at even level as one part, and let's see why there are no edges there. Okay? Why are there no edges at the odd level? Because, okay, if you take level 3, there are no edges because we have verified this. But why can't you have an edge between a vertex at level 1 and level 5? We argued this.
Right?
They are in consecutive levels or at the same level. So, the odd level and the even level vertices will form a partition because of this property. You need this property. Okay, the non-tree edges are either joining vertices at the same level or vertices at the consecutive level. Conversely, if you find such an edge, you want to produce an odd cycle and say that the graph is not bipartite. So what would be an odd cycle?
The path from S to that vertex, that edge, and then the path back to S.
Yeah. they may share something, right? So S to U and maybe S to V. So U and V are at the same level and you have an edge. So if these paths are disjoint, then yes, it's an odd cycle because whatever these distances are same, L plus 1. Otherwise, you can argue that somehow you can, I mean, at best they will just share some initial edges, and then from, since this is L and this is L, this is L minus something. I mean, these two distances are same. That's enough. This plus 1 is an odd cycle. Okay, so our algorithm will do one of two things. It's nice in that sense. It not only it will say it's bipartite, I can actually give you a partition and say here is the bipartition, or if I say it is not bipartite, I'll give you a witness odd cycle to say that this is the reason. So in some sense the algorithm gives a proof as well for somebody to verify. Okay, and it's all how much time it takes, linear time, because there's nothing much. BFS, it's order m plus n, and then you run through this for every edge. The D's are all sitting there. Okay, very clean, simple algorithm. You won't, I mean, without BFS, I don't know, are any of these kind of searches, it'll be very hard to think about how you would design such an algorithm, right? Okay. So let's look at the other depth first search. Again, as the name suggests, you go deeper and deeper and deeper and then come back and search, right? Breadth first search, look at all the neighbors of a vertex in some sort of a sequential fashion, then all the neighbors. In depth first search, you go, the moment you find a neighbor, I'm going to ignore my other neighbors. I'll follow him and find his neighbor, keep going until no longer possible, and then I come back and then explore my parent and so on. Okay, so let's look at it in an example and then see how you would implement it. So if this is my S, 2, 3, 4, 5. Hopefully it's sufficiently illustrative. So my BFS tree, for example, would start at S and then it will get 1 and 2. 1 has no more, so 2 will grow into 3, 4 and 5. That's how it is, right? So there are only 2 levels and you got the shortest paths, whole thing is connected. DFS will start at S it finds 1 and then goes to 1's neighbor 2 and then goes to some neighbor of 2, let's say it's 3, and then some 3's neighbor 4, 4's neighbor 5, and I don't have any more neighbor. Again, how do I implement it? The same idea of coloring works, blue, white, gray, black, but instead of a queue, you need a stack, because whatever you are adding, the latest you are going to explore. Whereas in the queue, we will add it to the end and say, okay, I'm going to finish my other guys first and then I'll come back to you, right? And queue is perfect for that because queue is first in, first out. Whatever I have added earlier, I'll explore that first and I'll add other guys at the end. Depth first search says, no, moment I find a vertex, I'm going to explore that. So it's like a stack, okay? So, because it's last in, first out. So after I finish with 5 and I find that there are no more white neighbors, I'll backtrack. And how do I backtrack? Stack is perfect for that. Because you finished 5, 4 will be sitting on the top of the stack. So From 4, see whether I have any neighbors to explore. No. From 3, from 2, and from 1, and let's just to illustrate something. Let's have some 6 and 7. So from so from 5, I cannot go anymore. From 3, 4. From 4, I could have explored anything else, but I chose to do 5. And then I backtrack. Then I come to 6 and then 7. So I come to 6 is another white neighbor, and then 6 is a 7 white neighbor, nothing else. I backtrack all the way, come here, backtrack, 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 and this will be my DFS tree. And as you can see that it's not really finding shortest paths, right? So BFS tree would be like this, because to 4 the shortest path is 1, 2, whereas this one is taking some 2, 3, 4. Okay. So the algorithm, the code is exactly the same, except instead of a queue we will use a stack. Okay. So I'm going to remove the distance now, because that's not. So what is the operation for stack? Push. Yes. So push. So we'll call it some S. Push little s into S. And while S is non-empty, use whatever pop. For every V, if color is white, push V into my stack and color it gray and make its parent to be the U. Okay. So if we want to implement this here, let's see what happens. So I will start, my stack will look like this, right? I will have S, and then I'm going to add 1 and 2 into the stack, right? So let's say I will add 2 and 1, no particular order. Because 2 and 1 are white, I will add it to the stack. Now I look at the top of the stack, which in this case is 1. So I'll go and explore. So 1's neighbors are 2 and S, so there's nothing to. Okay, so what did we do? So yes. No. So from stack I added S's neighbors. I will add it to the stack, which are 1 and 2. Okay, so let's see. Yeah, fine. So the parent thing should not be just U. So let me be careful here, because both of them don't get the parent. So we'll come back to this, the tree business. Let's see how I'm exploring. So 2 and 1 are added to the stack, and I'll pick 1 to remove, that's the top of the queue, and 1's neighbors are 2 and S, there's nothing more to do. And then I come to 2, 2's neighbors are, so 2 is removed, and 2's neighbors are 3, 4 and 5, right? In some order I've added to the stack. And then I decide to explore 3. 3's neighbors are all colored gray already, so there's nothing to do. And then 4's neighbors, 6 and 7, I'm going to add. 7 has nothing to do, 6 no more, 4. Okay, in the way I have drawn, actually 4's neighbors, okay, fine. So let me draw the tree from the stack and then we will figure out. So I have S and I add 1 and 2. Okay, I don't add 1 and 2. That is the difference. Unlike BFS, I just add the first vertex and then I'm exploring already. So what I would really like to do, okay, I'm not even going to use stack. Okay, stack, my implementation can take care of it. So what I will do is, DFS S. So everybody is colored white, S is colored gray. For V in, okay, adjacent S, I'm going to say color of V is gray and DFS V. Okay, it's a recursive algorithm, right? Color it V and explore V. I pick the first vertex, color it gray and just go explore V recursively, right? Finish all that and come back, pick the next vertex and keep doing it. After I am done with it, at this point I'm going to say color of V would be color of S, or let's call it DFS, U. Color of U would be black. Right? So the concept is the same, that I look at its neighbor, color it gray and go and explore that vertex. Right? So after I have done for use all neighbors, I'm going to color it black. Yeah. So it's a recursive algorithm which can be implemented using stack. So if V is white, yes, correct. If color of V is white, yeah. So we'll come to stack implementation later. But for now, this is exactly the way I drew the picture really, okay? Because I start with S, pick the first vertex which is 1, and then I get to the next vertex after exploring 1. So S has two neighbors 1 and 2. But what this is saying is, its color is white, yes, you color it gray, and then grow your DFS from here. Okay. After you finish it, I will come back and take the for loop will go to the next vertex. If it is white, I will color it gray and so on and so forth. Okay. So at this point, I color it gray and then I go and explore 1. 1 has neighbor 2 and S, but 2S is gray, so I'm not going to. So I'm going to add 2, and it says explore 2. There's nothing more to do anyway, so 1 has no more, right? So I'm going to explore 2, and 2 has again the same thing. 2 has neighbors 3, 4, and 5, but I will take 3, finish exploring 3. Then the control. See, if you have finished exploring from V, the control will go back to this, and then you will take the next vertex in the adjacency list and explore. Okay, this is exactly the backtracking. Okay, and the way to actually implement it is using a stack. Okay, but that is a system takes care of it. Yeah, so then how do you implement it? I start with S and say, oh, okay, I've removed S. I have to add 1 and 2 in my stack, but take, or rather 2 and 1, and take the first vertex and explore. So 2 will be sitting in the stack here, to remember that after I finish I have to come back here, right. There is a problem there because 2, if its color is, if its color has changed, then I won't even explore this. When I come and look at it, if it's color, so I will, this is right now just copying from the adjacency list, and I say that S has neighbors 1 and 2, okay. So it will just put it in the stack, and then it picks the first vertex and say, okay, 1, are you white? Then I'm going to color it gray, and put all, explore means what, I collect all its neighbors and I put them into the stack. And then I take the first vertex, color it gray, explore it, and eventually after I finish with one vertex, it will match this control, will come to the top of the stack. It might have become black or gray at that point, so I won't even explore it and move on, and eventually the stack will become empty. Okay, so a way to implement, so this is a clean way of seeing, a recursive way of doing DFS, but the way it will be actually implemented is take the BFS code and replace queue by stack, and that gives you an implementation, and hence the same running time applies, because it's every vertex gets into the stack and goes out at most once, and once you have it in the stack, you're going to look at all its neighbors and add it. So it's a sum of the degree, so it's order m plus n. But DFS explores in some depth-wise way, and somehow that has some other advantages which we will exploit for other algorithms. Okay, so so again it's order m plus n. I'm just going to, you can do the same thing if the graph is not connected, pick a white vertex and grow a DFS and get you can get this DFS tree. So in an undirected graph, now let's look at how will the non-tree edges be. Okay, let's first look at undirected. First of all, you don't have this notion of nice leveled tree, okay, like we had it for BFS. But you can, it's a tree, so you have a root, so you can talk in terms of levels, okay. So can you have an edge, cross edge like this? In a DFS, so you have, okay, this is a BFS tree, but suppose this is a DFS tree. Then I'm saying look at an edge in the graph. Can it look like this? Yes, because then you can ask, why did I not explore this guy here? Why did I stop here? Right? And even if this is gross, I cannot have, because when I would have, I am exploring this first, and then when I would have come backtracked, I would have explored this. It shouldn't have come under this child. So you cannot have a cross edge, right? No cross edge. In particular, this is going to be very useful. The leaves form an independent set. Okay, so no cross edge. I'm going to write this corollary 1. Right, because same reason, because if you have a leaf here and another leaf here, if there is an edge in the graph, then why did I not explore it here? Right? the DFS would have just picked it up and here because so the leaves are independent. It's going to be very useful for some algorithms. If G is connected, okay, fine. No. Okay, let's define. So let's leave it at this. Okay, how else can a non-tree edge be? It cannot be a cross edge. You are talking about undirected graph. Can you have an edge like this? You can, because 2 decided to explore 4 first, and in the exploration of 4, 7 got in. So this is an edge from ancestor to descendant or descendant to ancestor. Okay. Take any vertex, all its nodes in the subtree are descendant vertices and its parent and anything above is ancestor vertex. Then a non-tree edge can be from here, from an ancestor to descendant. So there are no cross edges, there are edges of this type. And you can again figure out how in a directed graph edges will be. Same, you cannot have an edge from left to right because then you would have explored it in your DFS. But you could have an edge from right to left because maybe you explode this and then it comes. And yeah, and then you have edges of this type, right? Okay, so this is we want to look at an algorithm for this next time, but let me set the problem and let's talk about a cut vertex. A vertex V is a cut vertex if in a connected graph, let's say in a connected graph G, if G minus V is disconnected. Okay, so somehow it's a crucial vertex. Imagine that you want to do some work on that intersection, but so that means that vertex is out of use, but still you want to make sure that everybody can reach everybody else. So you have to choose your non-cut vertices. So I want to know whether a graph has a cut vertex. Okay, so and if there are no cut vertices, it is a little more highly connected in some sense. Okay, so what would be, first of all, what would be a simple brute force algorithm to do this? Right? Take any vertex, remove it, and look at the remaining graph. We know how to check whether it's connected in order m plus n time. So that would give us how much time? N into m plus n time, because you just remove every vertex and check for connectivity, right? Yeah, so next time what we will see is using DFS. I have looked at the DFS tree, then somehow with some additional information which we can compute as we grow DFS, we can check whether a vertex is a cut vertex or not. Okay, so one thing I'll let you think about, we can, when will a root be a cut vertex? and that will give us an idea on how I can recognize any other vertex as a cut vertex. Okay. So we will give an order m plus n algorithm without this n factor using DFS.
In the DFS tree, we have two branches for this, but they will be
Right? Because there are no cross edges. So the root has more than one child, then it will be a cut vertex because there is no way you can, because there are no cross edges.
So that can be back edges, right?
Back edges are going from ancestor to descendant. Right? So my child or my grandchild to my grandparents. That's the way back edges are. I mean, think about, suppose I have, then this is a whole subgraph, this is a whole graph. Can you have an edge here? No, because if there is an edge, I would have, grown this part of that tree here itself.
So from 2, let us say there is a H to S.
Yeah.
And 2 are connected, and somebody from the right side also is like that.
I see. So you're saying 2 is connected to S and somebody from here is connected to S. Still, I'm talking, when you remove S, it's gone. S is such a crucial vertex. Yeah. Somebody from here, yeah. So when you remove S, there is no connection here. Yes, through S, there will be paths. I mean, it's already there. Right. So,
But they can be an edge from
no, you cannot,
No, yeah.
because then I would have grown my DFS tree here. Okay. So, root is a cut vertex if and only if it has exactly one child in the DFS tree. Okay. So now use these ideas and think about how can any vertex be a cut vertex, right? Somehow if I remove that vertex, guys below me cannot reach above me. When will that happen? What sort of, so I mean, that's more or less what it is, but we will see what information we need to compute additionally as I go along in DFS so that you can quickly check whether a vertex is cut vertex or not. Okay, next time.